无所，请取出话筒。
Hello, testing. Okay, good afternoon to everyone. So I have returned your assignment one. Later we'll discuss about it. After discussion, you think that the marks is the sum is there or it's not appropriate, you come and see me after class. But I will try to tell you give mark first. And then assignment two is due today, and assignment three is out already. Okay. Yep. Yes, so sorry about that. We have a weekly assignment because otherwise we are not sure on how you're gonna perform in the final exam, right? Because we got like 7 topics. That's quite a lot of them. Okay, so please bear with it. This is the second last already. This is the good news, right? Second last. After assignment 4, then you will be prepared for it. Just for example. Lecture is like 14. So we are over half already. That's why you will feel a bit technical, start to feel a bit technical, and maybe a bit fast, relatively fast, because it's going into some topics that you haven't ever seen before. Okay, so I encourage you to ask questions to slow me down. Okay, otherwise I will like pretend that you know, right? Because you don't answer me or I don't know you know or you don't. So please ask to slow me down because I get feedback that some students say it's getting faster, right? Okay, so please slow me down if necessary. Okay? Or ask me to repeat or whatever. Okay? Yeah. Otherwise, I see your face, okay, then I go, okay, fine. So please feel free to slow me down. What else? Okay, another extra thing is one of your classmates wanted to promote their community service so that him will come at 4 p.m. at our break time. Are you okay with recording? Maybe they are gonna record you guys. Is it okay? Is it okay? If not okay, then I tell the classmate no recording for promotions. You guys okay with recording? Okay. Okay. Most of you okay. Anyone say no? One of you say no, then we say no. If none of you say no, then we just let them promote their stuff. Okay. Everyone okay? Thank you. Yeah, so I think everyone here will go through community service, right? Yeah, so you will know how to support each other. Yeah, what's the need? Okay. Let's continue then. I found that people are pretty confused with primitive roots, right? So I make up some quick flowchart or summary. Yeah. Okay. So how to find primitive roots? Okay. To find one of them, you start with number 2, right? Okay. If it is relatively prime to P, if not, you found the next nearest one, and then you go on. And then we learn in a class on examples, right? 2 is almost always primitive root. Okay, for the P, but sometimes 3 or 5. So you need to try it out. But first thing you do is 2, then you have 2 first. If you can find one of them, actually you can find all of them already. Okay, so how to find all of them? You look at the powers of okay, you look at the powers of one of the primitive roots. Okay, and then raise it to the power that's relatively prime to 5p. Okay, so this 5p is very critical in this topic here. Okay, so meaning the number of integer that's relatively prime to p. And this number is pretty important. Okay, that makes sense. Yeah, and moreover, this power of r, right, will calculate for you the 5p as well. Okay, we'll calculate the 5p for you as well. So I mean, not just calculate. I mean, it shows you what are the 5p elements inside it. Does that make sense? So if you raise this r to 1 up to 5p, it will form the reduced residue system, meaning what? All the integers that are relatively prime to P, then you will find them as well. Does that make sense? And you can find all, so from one primitive root, you can find all relatively prime integers to P, and you can find all primitive root of P. And there are two things you can find from this primitive root. Okay, very special element here. So far, okay with this part here. Okay. To start with the first one, you really have to try. Okay, that one no choice. Again, you have to start with 2. Is it that order of 2 equal to 5 or not? If not, go to the next one, 3, 5, 7, up to before. Order before. Or element that are relatively private. Okay. And then we figure out what are the elements that has primitive root. Okay, not all the, we still remember from yesterday or not? Not all the integers have primitive root, right? It appears only in these form. Either n is 2, either n is 4. These are very special even power of even primes. And next one is power of odd primes. Okay, second one is twice the power of primes. That's it. Okay, that's it. Yeah, only this integer has primitive root. So only this integer will benefit, okay, will enjoy privilege of uh, finding the reduced residue system using primitive root. Okay. Otherwise, you have to just list. Okay, and the story about odd prime is like this. Okay, why powers of odd prime primitive root? First, you prove that every prime has a primitive root. Okay. And here is every prime. Okay, so in this previous statement here, these statement here, sorry, I should use other. So this condition here actually include all the prime. Did you realize? Okay, 2 is in there, 3 is in there. Why is 3? 3 belong to part C, and 5, 7 belong to part C. Okay, so even prime all of them are in there. Okay, and then we have this condition that we discussed last time. So you can take this primitive root and then ask what is the order, what is the order in p squared, okay, or p squared. So either it's p minus 1, either it's p squared minus p. Okay, but here we only care about odd prime. Okay, we only care about odd prime here. Okay, so if the order of r is p squared minus p, this is exactly 5p squared. So meaning what? R is a primitive root of mod p squared. But if it's p minus 1, then it's not 5p squared. Then it's not a primitive root of p squared. But then you just add p to it, it will become a primitive root of p squared. And then similarly, you assume odd prime again. Then this r or r plus p here will continue to be a primitive root of p. Okay, so now I wanted to try and prove to you this part, and maybe I'll try and prove this part. Okay, why this part is true. Yesterday we give you an example, but we didn't really show you or verify it to you, right? Okay, because when number get very large, right, taking power could be very troublesome. Okay, so we try to show you using definition way. Okay, so let's see how it goes. See, is everyone comfortable with this? Okay, so we're going to show this part here. R plus P is a primitive root mod P squared. Okay, so let's assume this part. Let's write down the statement here. If then R plus P is a primitive. Okay, so maybe we can ask, what do we want to do actually? Okay, what we want to show. Okay, we actually want to show that order of R plus P mod P square is equals to 5P square. Okay, so this is what we wanted. Okay, if it is true, then it is a primitive root. Okay, so let's start with the assumption here. Okay, suppose the order P square R equals to P minus 1. Okay, then what does this mean? Order, what's the meaning of the order? You take R to the power P minus 1, you get 1 mod P square. Okay, so how? Okay, now maybe we can consider another guy. Not that R plus P actually is R mod P. Okay, R plus P is R mod P because P is congruent with 0 P. Okay, so in this case here, R plus P is also a primitive root mod P because it's R is a primitive root mod P. Okay, maybe I need to add an assumption here. Suppose R is P. Okay, so in this case here, we know two things, right? Still remember, if we start with a primitive root mod P, the order of that thing mod P square is either P minus 1 or P times P minus 1. So if we want to show order of R plus P is 5P square, which answer we want? Which answer we want? Two possibility, right? Which answer we want? That's correct. That's correct. 5P square. Forget to calculate 5P square. How to calculate 5P square? 5P square is what? P square minus P. Okay, so this is the answer we want. Okay, so we need to prove that this cannot happen. The left one cannot. Okay. If the left one cannot happen, then so meaning it suffices to show that order P square plus P is not P. Okay. So well, I mean, like we just check. Then we just check what is this. Okay. R plus P to the P minus 1. Yeah. So we try and evaluate what's this. Anyone know how to expand this? Maybe if I give you 2, you know how to expand. But how to expand for different degree? Um, well, there's something called the binomial theorem. I'm not sure how many of you see it. If you don't see it before, you just take it for granted now. So what you have is, definitely you have R to the P minus 1, and then you have a mix between power of R and P. Can you imagine? Yeah, okay. So how they get mixed? So you can consider like A R to the P minus 2, but then you mix with a P, and then you slowly decrease the power of R and then increase the power of P until you will get P to the P minus. Okay, but this comes with coefficient. Okay, so but there's a nice way to talk about these coefficients. These are called the binomial coefficient. Okay, so binomial coefficient, for example, this part you left with P minus 1, and then the other part, actually you are making choice P minus 1 over 2, like that. Okay, and blah blah blah. And then this one is coefficient. Okay, if you don't believe me, maybe you can try like what is x plus y squared. Okay, is x squared plus 2xy plus y squared. But how do you get this 2 here? It is actually xy plus yx. So there's a choice here. Okay, you can pick x first and then pick y and then you pick. Okay. But this is not important. Okay, this is not very important, but the important part is this form here. Okay, what happened to this form after modding out by p squared? Okay, the most important part is what happened to this form after modding out by p squared? Because what we really wanted to know is order p squared. Okay, so we want to check whether this is 1 or not. Okay. So what can you see here? There's a lot of terms disappear after p squared. Right, because p is getting larger at the third term, right? Here we did starting at p squared, and then p cubed all the way up to very high. So meaning what? You only just left with 2 terms. I think the other term you get killed by p squared. Does it make sense? Because these are multiple of p squared. Okay, so what you left with is r to the p minus 1 plus p minus 1 times p times r times p minus 1. Can we further reduce? What do you think? Can we further reduce this term here? Any more p square inside your term? Or p square? P times p times r to the p minus 2. So you can reduce some more. Okay, you can reduce some more until you get 1, 1, yeah. What am I doing here? Okay, so rp minus 1 minus p times r times p minus 2. Okay, but still remember what is r to the p minus 1 here? What is it? What is this? Remember what is this? This is your assumption. Order of r at mod p squared is p minus 1. Okay, meaning what? This term is number 1. Okay, so what you really left with is 1 minus p. That's it. Okay, so so if you don't want, okay, if we don't want this p, this order of r plus p is p minus 1, meaning what? We don't want just left with 1. Okay, so we don't want it to just left with 1. So meaning we cannot make this guy disappear. We have to argue that this guy will stay there. Yeah, something like that. Okay, makes sense so far? Okay, we don't want this to be 1. If it is 1, then your order should be less than or equal to p minus. So then suppose for contradiction, suppose it is 1, then we'll get some contradiction. And suppose that it is 1. Okay, I think almost most of the proof I present here is contradiction, huh? Yeah. Okay, so maybe this is one of the things you will learn from this class. For proof by contradiction. Okay, so if we assume that this is true, then this will imply that the term should be 0. Okay. But then this is 0 means what? The other, if this the other term here is 0 means what? It means that actually r to the p minus 2 congruent to 0 mod p. Okay, well, this is nothing but just because this will imply that pr p minus 2 is a multiple of p square, then you cancel p from both sides. Okay. Okay. So, but then can this be true or not? Is this possible? What does this mean? What does this mean? This means that r to the p minus 2 is some multiple of p. So meaning p divides r. P divides r. Can b divides r? What is r? R is primitive root. How do you find primitive root? Relatively prime. What other than relatively prime should be number less than p? Can a number divide something less than it? So can 4 divide 2 or not? Cannot. Okay. So, but p cannot divide r, as r is a primitive root of, or if you like, r is less than p actually. Okay, so I think we are good. So as the order of p squared of r plus p is not p minus 1, okay, so we can conclude that it is another case. Okay, so we can conclude that order of p squared of r plus p is equal to p times p minus 1, okay, which is 5 on this one. Okay, so r plus p is a primitive root of p squared. Okay, so I present you a method that without doing the order checking, the taking a lot of power, I can prove to you that it is a primitive root. Does it make sense? Okay, so sometimes proof is more efficient than calculation. Okay. Yeah, imagine the number get really big. It's very hard to do hands-on calculation. Okay, so far so good. Okay, can remember if r is not a primitive root mod p squared, then r plus p is a primitive root. Okay. So how do you prove it? Actually, you need to use this expansion to help you. Okay, binomial expansion. Okay, how people find it acceptable? Hard, mind-blowing, shocking. How people do it? Super good, good. Some of you good. How about the rest? Not good. Not good. If it's not good, I mean, I tell one of the students, right? I guess in the university, right, there's another skill you need to learn. Okay, you need to learn to communicate. Okay, you need to learn to do research. Yeah, so you need to communicate. Nowadays, you rarely do research by yourself. Okay, because the knowledge is already advanced to the state that you need different area to help you. Okay, so you need help from uh, different different field. Okay, different expertise. Okay, so you need to learn to express yourself clearly, okay, and then understand what people say. Two things. There are two things you need to do here. Okay, it's not like in high school you just read the textbook by yourself, you answer the question. Not like that. Okay, if it's like that, then you can never do research. Okay, even the old days like Newton, whatever, they also go conference. They also talk to people actually, but maybe not too often, but definitely they talk to each other. That's why Newton and Linus they come up with the same calculus because they heard about the idea, right? And then they try and write it out. You understand? Okay. So if you have any question, so make sure you ask. Okay. I know that some lecturers don't like. I do know that. I noticed that. But then for me, I guess you have to grab this chance and we say kacau, like disturb me, disturb me. You have to disturb me. Okay. Otherwise, I go in my tempo, then you will like don't know what's going on. Okay. So make sure you disturb me. Okay. So that I know what are you thinking, then I can try and uh, adjust my explanation towards your answer. Okay. Okay. So please talk to me. Otherwise, go my own tempo. If in this case, should we do a second proof? Should we do a second proof? I wanted to do a second proof. Or you guys want or not? If you don't want, then we continue with new stuff. You want to see a second proof? Okay. 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 So let's look at a second proof. Okay, what I wanted to prove is this. So maybe first time you see this is quite weird. YR is odd, then R automatically a primitive root mod 2 times P squared, PK. And then when R is even, YR plus P squared is a primitive root mod 2 times P squared. Okay, PK. So this primitive root is concerning about the type of integer that is a twice of power. So this is the fourth case, right? Fourth case in our list. Okay, so this is the fourth case. Previously, this is the kind of the third case, right? First case. Is it? Can we say that? Before third case. Okay, before third case. Because you once you get the third case, where's my table? Yeah, once you get the P square case, and then you get the all the PK case. This proof is it? Oh, I'm not showing this proof to you, huh? This proof is wait, let me see. Let me think. So where's the segment for PK one? There's one proof that I skipped that I don't want to show you because that proof is a bit involved. Let me check. Let me check first. Yeah, so this proof is a bit involved. Let me see. It uses a mathematical induction, so that's why I skip it. Okay, so I'm not going to show you this direction. Okay, what I'm going to show you is the fourth case. Okay, so how do we get the fourth case here, which is twice of the power of prime. Okay, what I'm going to show you is this fourth case. Okay, so this one no need induction. Okay, again, let's try. Okay, let me try it. Okay, so well, to prove something, you must get your statement out first. Okay, this is a very important thing. Okay, even when you want to explain certain thing to people, you need to tell people what thing you're gonna explain first. Only start explaining. Did you met a people never tell you what is happening and then start blah 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 blah. This guy like what this what happened, and then you don't know what is going on. Okay, so you try to give people headline first. This is what happened in newspaper, right? You see the headline first. Only you go and read the news itself. Okay, it's not like you never read about the headline, then you go into the news. Today what happened? What happened? This guy killed that guy, accident. Okay, so get the headline first. So theorem. And the top prime and R be primitive root modulo PK. Okay, so first case, if R is odd, then R is also a primitive root mod 2pk. If R is even, then R plus is a primitive root mod 2. Okay, so we're gonna present you a proof that without doing the power calculation thing. Okay, so meaning we need to dissect the structure of this number. Okay, so proof. So well, let's start with the assumption you have. Suppose R is a primitive root mod pk. Okay, so what does this mean? Okay, so well, I think mathematical proof is very easy. You tell me some assumption and then I try to write out what it means first. Okay, and then see where we go. So the assumption is R is a primitive root mod pk, meaning what? R to the phi pk, the order of R should be phi of pk. That's it. Very simple. Nothing special. PK or PT? PK. I don't know why I put PT here. Okay, PK. And then what? More than that, right? The order means what? it's not just the integer that made your R to 1, it's the least, the smallest one. Okay, so meaning, still remember when you do calculation, no other positive exponent smaller than this number will have the property. Okay, this is the first one, the first exponent that you reach, the number one, the identity, multiplicative identity. Next, then we will also know that actually R to the 5 of 2pk is congruent to 1 mod pk. Okay, why? Because 5 is multiplicative. Okay, so 5 is multiplicative. So I can split up this 5 times 2pk. So it's 5, 2 times 5. Because p is odd, okay, so 2 is even, so these are relatively prime. I can split up by multiplicative property of 5. Okay, so far so good. Okay, so from R to the 5pk is 1 mod pk, we get that R to the 5 2pk is 1 mod pk. Well, so if R is odd, then R to the 5 2pk here is congruent to 1 mod 2. Does this make sense? Mod 2 means what? Either you 0, either you 1, right? So either you are even, either you are odd. Can you believe that if no matter what power I take for odd number, it's still odd? 339, 93, 27, 27 times 3 is what? 81. Okay. So, well, I mean, a very quick proof is like this. So you take 2k plus 1 to the power of something. Okay. Yeah. So this plus 1 here will always stay there. And plus 1 will always stay there. And then the rest will have a power of 2. This is very important. So you will get 2 times some jump here plus 1. Okay, you can put this. Okay, if not, you can accept this. So you can see that you got these two congruents, right? And then these two things is relatively prime, right? What can you use? Chinese remainder theorem. Okay, very good. Okay, so by Chinese, so this is using what we have learned. Okay, by Chinese remainder theorem, this solution here will solve a congruence or the unique solution for R to the 5 2pk congruence to 1 mod 2 times pk. So that's why this special number here pops up from the Chinese remainder theorem. Okay, so that's why it works for this 2. Why suddenly got this 2 coming up? Okay, it's because of this. Okay, so then we will argue that. So now we got a claim here. So we claim that no smaller power of R is congruent. Okay, now this is how we settle all the power before this is taken on. So we claim that there are no smaller power of R is congruent to 1 mod 2pk, as such a power would also be congruent to 1 mod pk. Okay, so any power that less than 5 pk, right, cannot go to 1 mod 2 pk. Otherwise, if it is 1 mod 2 pk, it's definitely 1 mod pk. Okay, so meaning you will get something smaller to 1 mod pk, then you will have a contradiction to this statement. We claim that there's no other contradicting that the assumption that R is a primitive root of. Then maybe I put a reason here because 1 mod 2 pk will imply that it is also 1 mod. Okay, so you get something smaller. Yeah. Okay, so then it follows that R is a primitive root mod. Okay. Okay. So how about the other case? Okay, the other case is very similar. Okay, very similar. On the other hand, if R is even, then what we did is R plus PK is odd. So we go back to the first case. Okay, so we go back to the first case. So hence, R plus PT here to the phi of 2PT should be 1 mod 2. Okay, it's also odd like last time. Okay. So since why do we plus a PT here? Because actually R plus PK here is congruent to R mod PK. Okay, so that we can retrieve the similar congruence, that is R plus PK to the 5 of 2 PK is congruent to 1 mod PK. Okay, so we retrieve the case where R is odd. Okay, the same argument will come. Yeah. Okay, so why we plug the PK, not a P like last time? Because of this segment. Then we make it return R after going out line. And then you will follow the argument. Like R is odd. Yeah. Okay, so this is one way to avoid calculation instead of doing all the checking. Yeah. Any questions so far? Any question? Do you have a brief idea on why these 4 cases matter? Okay. 2 and 4 we show it by example, right? Just calculate for you who are the primitive. Okay, and then the rest is you can show it by proof. Yeah, how we obtain it. And then for the other direction, meaning if it is not in all these cases, you don't have primitive root. We also didn't prove. I also didn't prove to you, but it's in the notes if you want to check. Okay, it is this statement here. So if it's not these 4 cases, it is these cases. Okay, where is it? For this, for this, this, for, hey, where is it? Disappear. Disappear. You still remember which statement is that? The one I talked to you yesterday. Yeah, this one. Okay. So this statement will throw out all the other cases. And because just now we just showed to you that if you are in those cases, you have a predictor. And we have if it is not when it is not when it is not when it is not these cases. Okay, so meaning right, if your n has a primitive root, it must be prime power or okay. 2 and 4 is this relation. Okay, because 2 is a prime, then 4 is 2 times 4. 2 times 2, sorry. Or twice a prime. Okay, I don't choose to present this to you because why? This proof consists of like a few parts actually. Yeah. So I don't want to confuse you again. So I try to present some proof that maybe use only one or two parts at most, so that at least you know the idea of connecting these arguments. And then this I think it connects more than one, more than two again. There's Euler theorem here, and then contradiction used here, and then you need to use LCM here. And then Chinese remainder theorem is the other of them. And then multiplicative structure of phi. And then relatively prime stuff. Yeah. Quite a few ideas coming in here. Okay. So if you can learn the two that I told you, maybe you can read about this. Okay. Yeah. No extra strategy here, just that there's a lot of ingredient inside here. Okay, if you are curious, okay, you can read this. Okay, any questions so far? Up to here. Okay, so whatever we are mentioning just now, we're actually just building this theorem. Yeah, this theorem. What sort of positive integer has primitive? And then how is the root looks like? Question? Any question? There's no stupid question in this world. Um, Even the most prominent mathematician, right, start asking question by asking stupid question. Okay, after stupid question, you will know that what you are lack of, and then what are people considering, and then you start mind change. Okay, and then straight away you can solve like maybe very detailed or very straight to the point question. You understand? Okay, because sometimes it's not that you don't know, it's just that you live in a wrong world. I mean, you start with a wrong assumption. Okay. Yeah, this is typically what happens in real life. You are actually calculating different stuff. You are not wrong actually. You are calculating different stuff. You are doing different stuff. But in others' eyes, you are wrong. You understand? And so, like a teacher or what is trying to discern this, okay, trying to see why the student work like this. What's wrong with it? Not wrong. What happened to it? So this is one of the skills that I have to learn. Okay, if you want to be a teacher, maybe you have to learn. Okay, if no question, maybe we start the last part of that chapter 4 before we go to chapter 5, which is index arithmetic. Okay, index arithmetic. But before that, maybe I can remind you a bit on log to get you a right idea on log before we jump into this index stuff, because these are very related. Maybe I go here then. Yeah, because these are very related. Well, wait. Okay. So, how do you understand about this thing here? Of Sing's high school, how do you learn this guy? There's another way to write this, right? Okay, another way to write this is a log of 8 to the base 2 is 3. Okay, learn this before. Okay, so try and look at what happens here. So inside this two equations here, right, there's new thing coming up other than the number one called log. So meaning log is a process. I mean, it's a function. Okay, it's a function. Okay, so this function take in two things. So take in 2, take 8, for you 3. You think about what is this 3? Yeah? What does this 3 have to do with the 2 and the 8? It tells you how many times 2 times to itself you get 8. Make sense? Okay, so So this is what log do. Log study the exponent of 2. Yes. And then I think you learned in school that there's log property, right? Log of maybe base 10. A plus B should be. Or no, I'm not wrong here. Or am I wrong? It's log AB. Maybe okay. It's log 10A plus log 10B. So if you think about this way of reading this, does this equation make a lot of sense here? This make a lot of sense here? No, still no. Okay, so maybe AB is something right equals to some M. Right? So log of AB. Okay, so maybe sorry. I should write like this. So 10 to something log AB should be equals to AB like that. Right? Yeah. Okay. So if on the other hand I know that what is let's say 10 to the log 10A uh, times 10 to the log 10B, it is just A times B. But then on the power side, what happens? If you know, you can combine this base number, right, by adding up the exponent. Okay, so that's why you get. So the multiplicative structure here become an additive structure on top. Okay, this is the other way. This is a different thing, huh? And multiplicative structure become addition because the multiplicative function is multiplication split to multiplication. Phi a b equals to phi a and phi b. Yeah, but this one become addition. Okay, very special thing. Okay. Okay, so far okay about this log. Okay, so what we're gonna do is similar here. Okay, instead of doing log 10, we will do log with modular. Okay, so the equation here will become modulo. Okay, so the equation here will become modulo something. Okay. But we still have this kind of log structure here. Okay, which we call the index derivative. Okay, so let's see why is it so. So let's see before we told you the definition. Let's look at one example here. So every positive integer less than 17 is congruent to 3 to the a for some a. Therefore, find this a for each of these 16. Okay, so basically what we're gonna ask you to do is to find uh, 3 to the something congruent to like 1 mod 17 or congruent to 2 mod 17 or congruent to 3 mod 17. Every positive integer, so up to 16. Okay, can you try and do it? See what's the power to get for 1 up to 16. I mean, for the first one, it's easy, right? Just take A1 to be long. For second one is not too hard as well, right? Second one is quite hard actually. Okay, maybe there's one is not hard. So 3 square is not hard. You can get 9 mod 17. Okay, does it make sense? Can you figure out for the rest? I'll give you 3 minutes. Try and figure out for the rest. Okay, try and check for all number in between 1 up to 16. Sorry? A1 is not 1, huh? Sorry, yeah. Okay, let's think this. A3 is 1. Good. A3 is 1. Yeah. Okay. A1 equals 1, I think is kind of kind of kind. Okay, I give 2 easy examples. Try and do the hard. Okay. So how you do? Okay, instead of asking who gets 1, 2, 3, right? Why not try the other way? Like, just compute what are x 3, 1, 3, 2, 3, 3, and then so on. Okay. I think this one is easier. Maybe I duplicate this. Okay, why not we just compute 3 up to different powers? Yeah, then you'll be very quick. So maybe 3, 7, 3, 8, 3, 9, 3, 10, and then 3 to the 11, 3 to the 12, to the 13. Anyone manage to calculate all? Does anyone manage to calculate all? Okay, if not, we can try this. So this is 3 mod 17, and this is 9 mod 17. And this one is 27, which is 10 mod 17. And then you go on. Yeah, maybe you can check as well. I will leave this to you and then continue. Okay, and then you get 1. Because if you notice 3 to the 8, you get minus 1. Okay, so what can you see here? You can see that these numbers are not repeating. Why? If you still remember what is the primitive root of 17? 3 is a primitive root of 17. If you take 3 to different power, what do you get? A reduced residual system. But in this case, positive integer less than 17 are all primitive, are relatively prime to 17. Okay, so this is the complete list of reduced residual system. Second law is promising. Second law is mutual. Huh? Look at this theorem here. Look at this theorem here. Look at this theorem here. You still can recall two powers of A are the same if only if I and J are mod order of A. Okay, so meaning these I and J, these power are unique. They have to be the same. If there are some number that less than order of it, okay, they have to be the same. So it's unique. Okay? So if something is unique, then we can define this. Okay, so let R be a root of a positive integer m, and let A be an integer relatively prime to m. Then there's a unique x such that R to the x congruous to n of m. It's unique one. Okay. So in this case here, this x will be less than 5m and then greater than 1, and then we'll call this an index of A. to the base R modulo n. Okay, denoted by in Rn. So this is the log. Okay, index. And sometimes the log will solve it. Okay, index the base R modulo n. A bit unfortunate, huh? There's no m inside this notation. I'm not sure why. Because this m is quite important here. Because R could be a primitive root for m, but not the other. Understand? So I'm not sure why there's no m here involved. But make sure that the question will tell you what's the m and what's the primitive root before ask you to calculate. Okay? So m is pretty important. I'm not sure why missing m in the notation. I think textbook also like that. Should be appearing somewhere, but I'm not sure why. But as long as we write down this R should be a primitive root. Okay, so that this x will exist. Can exist and unique. Okay. Right. So in this case here, if you look at this list, maybe I can test you about this notation. Let m to be 17. Okay, so this is an example. Can you find me in 3, 3? 1? Okay, good. In 3, 16. Huh? 8. Good. Okay, so this is the 8. This is the 1. Yeah. And then maybe in 3, 7. 11. Okay, 7, 11. Okay, good. Okay, so this will help us solve congruence like this. Something like this, it could help us solve it. So let's see how to solve it. Huh? So you can see this congruence is a bit different from what we have learned. Like for example, the linear congruence, the Chinese remainder theorem. Okay, because there are more power here already. Okay, so we need this kind of things to help us to deal with it. So let's see how it helps. Huh? Well, one way to do this question, do you know how to do it? One way to do it. Because there are really only finitely many things you can try. You can try brute force. Yeah, brute force meaning you plug 1, plug 2, plug 3, plug 4, and then calculate do you get 11 after taking power to 12 and then times 6. Okay. Otherwise, we're going to use this method. Okay, using primitive root method here. Okay, so primitive one way of using primitive root is to solve this kind of congruence. Okay. So note that 3 is a primitive root of 17. Okay. So this in this case here, this involves what kind of integer have primitive roots? If the modulo n doesn't have primitive root, then you cannot solve it this way. Okay, but in this case, it has a primitive root. So we can rewrite everything in terms of power of 3. First, just now you look for the index of 6, should be 15. Okay, so if you go to this list here, and then you found 3 to 15 to 6. Okay, and then on the other way is just some random x, right? So we just make it a random power of 3 to 12. Okay, congruence to the index of 7 should be index of 11 should be 7. Okay, base 3 or 17. Okay, so why do we do this? Because we know that if the power of 3 are congruent to each other, we can talk about their power. We can talk about their exponent. Okay, this theorem here. We're going to use this. So this one implies that 15 plus 12y congruent to 7 mod 5, 17, okay, which is 16. Okay, then from here, you make it a linear congruence. Okay, from a power congruence with power, you make it a linear one. Okay, so this is the advantage. Okay, to go to the power. Okay, so you get 12y congruent to negative 8, which is congruent to 8 mod 16. And then you can further simplify, right? Okay, because everything is divisible by 4. Okay, so this whole equation here is divisible by 4, so it becomes like that. Okay, 3y. If you're curious how I get this, so it's just because this modulo will give you 12y equals to 8. Sorry, minus, oh no, equals to 8 plus a multiple of 16. Okay. And then what did you see? You can, what can you do next? What can you do next? What can you do next? Huh? What can you do next? What? Say again. Oh, yeah, sure. But then I want to solve y, right? Is there a better way to solve this y? Multiply by 3. Okay. So you multiply by the inverse both sides. Okay, why there is an inverse? Because 3, the GCD between 3 and 4 is 1. So 6, which is congruent to 2 mod 4. Like that. So I think we are good. Oh, not good yet. Because we need x, right? Instead of y. Okay, we need x instead of y. So this implies that y is equal to 2 plus 4k. Okay, for some k. Okay, but this y could appear in between 1 to 16. You will get 2, 6, 10, and 14. So your x is like 3 square, 3 to the 6, 3 to the 10, 3 to the 14, okay, which is 9, 15, 8, 2, mod 17. Okay, so far so good. Okay, so these are the 4 possibilities you can queue. I mean, if you like, you can do some sanity check here, whether this answer is correct. Okay, check the form. Any questions so far? Any questions? No? Okay, we take a break. Okay, after the break, we will do last question on this thing here, and then we'll go to next one. Okay, so let's break until 4:70.好，等一下我会解释等一下再过来。之后我们会讨论这个什么？可能第3个小时我会讨论吧，或者下个小时我会讨论。嗯，好，没事。
他可以以后留在讨论是吗？
没有，就是在第3个小时或者第2个小时我会讨论。下堂课或者就是
什么这样？
不是下堂课，就是下一个小时
下一个小时会怎么样
我会讨论assignment。
？Assignment？
Yeah，
哦，
啊，
考试的难度跟 assignment 比怎么样？
应该差不多一样。
这么简单吗？
这个
没
Yeah
没有，你上去讲那么多 proof，哦，那就行。Oh my god！我前天复习了6个 hours 的
哦，真的
proof，
吗？
一直在看 proof。
现在到大三了，脑子不好用，不如大一好用。
大一的时候一听就懂了，现
现在
在
大三我还得回
回去复习。
大3了，这么
啊，
脑子已经不好用了。
可以，
脑子不好用。
可以，很快啊。啊？什么？李爹啊，不懂哎，他没有跟我讲哎，你问他看。可以啊，可以，你可以跟他一起咯。
这里就是这样写的，它周期是4，然后就我觉得可以直接看出来。
对，OK，第一个我们没有介绍过那个 period 对
周期啊，
对，我知道。
period。
确实，我可能大概知道你在说什么，但是我们介绍过，所以我一开始不知道你在干嘛。然后第二个就是我看你的周期是无这个东西，这个可以背4个出。
对呀，还有雨伞嘛，还有雨伞就是第3个，然后
这样的。那为什么是498.3呢？
就是498雨伞的意思
这个符号我没有介绍过。
啊，但中国就这样讲。
中国是这样讲。OK，因为在马来西亚也没有这样。
哦，这
啊，对，所以最好，对，所以我们班上的教法就是你一定要写498乘4，就是1995等于498乘4加3啊，对吗？是不是啊？这样也可以表达。And then 给我想一下。呀，我觉得你就是用这个来讲，这一个是这个就好，你根本就不用说 period 的东西啊，因为这个词我们没有介绍过，所以如果你要打算用新的东西的话，最好是要解释。
我以为，因为就是在国内就不能教。
对，因为我们这里上课的方法就是所有的用到的东西，我们一定会在网上教过，这样。所以如果你能够像我刚才讲的，就是如果你能够把这个199写成498乘4加3的话，then 你的这个 term 就是这样子嘛，然后也不太对呀、然后这样也很难看啊，其实。
所以它就是第3个呀，1、2、3。
好像不是这么解的，这题，但是解法有问题吧？为什么？为什么？我想一下，为什么有这种周期性的概念呢？
就
就是
它
啊，
它那个最后一位数是成规律的呀，就是4个为组，然后刚好这是498个完整的周期，然后还是3个，然后就是1、2、3，然后说刚好是第3个周期里的第3个，然后它的个位数就是3。
这三个，这个永远对。你上面也是这样解吗？上面也是这个解法。
上面没有啊，因为这个是有那个周期性，我才这样解的。
什么说？但是这个周期性你也没有证明过，你只是看到前面5个就讲它有周期，
但是一般就这样，
没有要证明，
必须得证明。
因为它的周期可能更长啊，你可以想象，比如说 T9317可能8T，然后再因为就是这个周期性是需要证明的，你不能看前面一开始气就开始周期了，不可能，对吧？你曾经算过76了。
但是7，我记得7的那个周期，它就是
记得你怎么写？
就像那个总结的经验吧。
老师，我们那个 promotion 在门外了。
OK， 好，可以进来。好
3可以整出3个，如果位数加起来就也可以被3整。像我以为这是一个，就像3啊、5啊那种，这不也是一个比较常规的那个吗？对，就是它的一些基本的规律。
但是我们也没有证明过，但是我们帮你学过。
对，
嗯，
我以为它是像3可以被3整的那种是比较那个，但是相当于
这需要证明吧？需要证明，而且我们班上也没有介绍，所以就不能
除非你能够证明现场
你看过门打？
没有。
还没有点，你可以看一下我们怎么做。
还有这个不就是我把它的逆圆给算出来之后，然后
对
同理可得。
对，你没写，
就是写了一个不就
你写了一个吗？
写了呀，这儿等于3，这就折过来。
啊，
一个是写一个同理可得，是不是？
对，因为我不知道你在干嘛，一会儿其实可以。对，
因为这个方向。
对啊，
我说英文，你说中文。
OK 好，OK，等一下我讨论多，你再说。
我并没有
看看你
我认为好。
Hello. Yeah. We want to do a promotion.
Yeah, we have like a project and we do like a 1-minute ad.
Sure.
Is that okay?
Okay. Yeah.
Thank you very much.
Okay,
Can we
so-
borrow the mic?
Yeah. Sure. The community service is here. The promotion of community service here. So I will pass the time to them.
All right, everyone. So as you know, on YouTube, you have ads. We're introducing ads to classes. So that's a new thing we're doing here. For our project, we're opening up a kind of casino on campus. It's not a real casino. If you gambled before and you lost money, we're opening up a simulation casino. I mean, you guys are learning about escape theory.
Elementary number 3.
You guys are learning about elementary number 3. You want to be smart. You must know about probabilities, numbers. So you can come to our event. You can learn, you can gamble, and you can learn to not gamble in real life. Just gamble in our event, okay? So if you're interested, here's our publicity team to tell you what it is.
Right. So I know you guys are wondering, how do you promote anti-gambling by letting you gamble? That doesn't make any sense, right? So let me give you an analogy, okay? You guys know the story of a vaccine? You introduce a weaker virus to your body, and it's to prevent all future viruses. That's basically us. We're the XBAT vaccine. And we basically introduce you to a weaker version of gambling, which doesn't really get you hooked, but by losing, you'll get discouraged to gamble in all your future endeavors. So if you want to get a shot of the XBAT vaccine, come on down to B1B05 next Thursday, 19th of March, 4 to 9 p.m. Now, for those of you who did not understand the word I said, here's a Chinese version.
Chinese translation.
大家好，这是我们来推广一下我们 community service 社区服务的这一个活动。然后这个活动是由我们学生自己来组织的。然后我们的活动主题就是要告诉大家千万不要赌博。我们会设计一些就是赌场中的游戏，然后我们会让你一直输，就是永远不会让你赢。这种玩法就是鼓励大家千万不要去参与。
哦，还是有可能会赢的，还是得过来，还是有可能赢的有。
Tell them we have free pizza vouchers for everyone here. Free pizza vouchers.
就是说我们这个活动就是大家来参与是不用交任何费用的，然后我们还会
关注的就有一个
对，就是如果大家有 IG 的话，可以关注一下我们的社交账号，然后我们会给大家奖券。然后我们活动是我们下周四在 B1B05，就是在那个最下层超市旁边那个小室1B05，从下午4点到晚上9点，我们会有这个一些小游戏，然后大家免费入场，然后只要你能过来，就一定可以带奖品走。然后相信大家一定会获得一个难忘的体验和经历，谢谢大家。欢迎来了。然后我们的 IJ， 我想想怎么让大家来扫呢？那对，就是现在那个白板上这里写着 MUMX.BAT， 这个是我们的 IJ 账户，然后麻烦大家关注一下好吗？然后下周4如果大家有空对我们这个活动感兴趣的话，也可以过来玩，我们有奖品，一定不会亏待大家的。谢谢。
That's MUMX.BET. For those at the back who can't see, remember MUMX.BET. That's MUMX.BET. I'm going to leave a few pizza vouchers here. It's a first come, first serve basis. So, hey, after class, you can just help yourselves. Thank you so much for your time and attention. I'm not going to take away from this interesting number theories anymore. So, all right, thank you so much to the lecturer for giving us this time. Thank you guys so much. Hope to see you in the event.
Okay, thank you.
Thank everyone. You can go back to your
Yeah, please remember, come and get your pizza coupon. Otherwise, will be others. Okay. Yeah. So we'll discuss the assignment in the next hour. So after next hour, you can come and ask if you have extra question on your assignment or marking. So final question on this part here, we're gonna solve this congruence here, 7 to the x. 6 or 17. Okay, so you can realize that this x here appears on the exponent. Okay. So we're gonna use the primitive root method. Okay, we're gonna use primitive root method. Okay, so again, we're not that 3 is a primitive root of 17. Okay, so we're gonna set, we're gonna find everything in terms of 3. Okay, so the index of 17 should be 11, okay, as we computed before, and then 6 appear again. Actually, it's index 15. So then from here, remember the theorem that we can reduce this question to exponent, which is 11x congruent to 15 mod d. What's this order? Sorry, not order. This is 5, right? 5 of 17, which is 16. Okay. So in this case here, what do you get? Can you quickly compute this? Yeah, inverse of 11. 3. 3? Okay, 3, good. Yeah, okay. So yeah. So what do you get? 45, which is 730, yes. Okay, yeah, that's it. 45. So far, so good. Okay. So the idea here is you can translate anything on the exponent. Okay. Okay. So you translate anything on the powers of a to the exponents. Okay, that's it. Okay. So you make something non-linear to linear actually. Okay. Yeah. Because 2x is this thing is non-linear. Okay. This part here. Non-linear. And then you change to something linear. And linear is good. That's why you learn linear algebra. And you don't learn non-linear algebra. Linear algebra is good. So we learn things into linear. Okay. Non-linear stuff is really hard. And like non-linear PDE, non-linear partial derivative, differential equation. Dynamical system in particular. Yeah, I think tonight there's a speaker on PDE, right? If you guys want to join, MAT Student Council talk. Yeah, there's a PDE stuff, non-linear stuff, real life non-linear. Okay. Right. Okay, so before we end this, maybe I have to show you another slide on index. It is this thing here. I want to convince you that this index really works like logarithm. Okay, here is the property. Okay, so index of 1 to any primitive root is 0. Yeah, like log. Yeah, log of 1 is 0. Mod pi m. And then index of AB should be index A plus index B, index of A to the K to the K. Okay, and then this proof is very easy exercise. Okay, you can also understand well. Okay, yeah, if you like. By the way, proof is not important for the assessment. It's just important for your study. But if you equate your study with assessment, then this becomes not important. Okay, so if you really want to study a knowledge well, you really need to spend. But if you just want to pass or one, and you can. Two, and you can too. And for those who want to learn, you can learn a bit more. Okay, so before we close out this chapter, any question? I hope you get an idea on why we are learning primitive roots. Huh? Okay, so these will help us to solve exponent congruence here. Okay, congruence with exponent. But not every one of them, because you remember primitive root is very restricted. Only work for 2, 4, and then power prime, and then but these classes of integer is quite enough for the purpose of our most of purpose already. Okay, it's quite enough. Okay. If no question, then we will go to the next part, okay, which is called the quadratic residues. Okay, so we will enter a little bit intro to this chapter, and then we can continue again tomorrow. Quadratic residues. Okay, so what's this two words means to you? Any idea on these two words? Maybe separately. Quadratic. What's quadratic? What's quadratic? Quadratic equation. What's quadratic equation? Polynomial with our degree of 2. Okay, degree 2 polynomials. Residues. If you learn chemistry, maybe you know residues. Leftover. Okay, so something you take to degree 2 and then leftover. Quadratic residues. Okay, so let's see how we define it later. So in that case, I'm going to deal with degree 2. Okay, so in this case here, I ask you to compute. I give you P is 3, 5, 7, 11. What is the M squared for 1 up to P minus 1? So for example, when P equals to 3, 1 square is 1 mod 3, and then 2 square is again 1 mod 3. Okay, so you're taking square, and then what's the leftover? Okay, you take square and then see what's the leftover. Why we don't consider 3 again? Because if you consider 3, 3 is 0. 0 square. And why you don't consider 4? You go back to the case of number 1. Okay, so that's why we just compute these two up to P minus 1. For other integer, you are just repeating. Okay. How about for P equals to 5? Okay, what is 1 square? What is 2 square? What is 3 square? What is 4 square? Can you quickly see? 1, 4, 4, 1. Okay, so what you notice is out of these 4 numbers, only 2 numbers appear as the residues. Okay, anything square after squaring, it reduces to 1 and 4. Okay, so far, so good. Okay. Should you try 7? Can you try 7 yourself? Yeah, I give you 1 minute. Very quick. See what's the residue you see. Definitely. Okay, did everyone see this? 1, 4, 2, 2, 4, 1. Okay, yeah. Very good. I see some of you see that this thing is symmetric. Right? This is not accident. This is not by accident because you can rewrite the other half as a negative. Yes, for example, 4 is like -3 squared. And 5 is -2 squared. And 6 is -1 squared. Okay, so it's not a coincidence here. Okay, so yeah. Okay. What else you can observe here? Anything else you can observe here? Okay, maybe one not obvious one is 4 will appear twice, 2 will appear twice, 1 will appear twice. Always in come in pair. Any other observation you can do? Maybe so far like that. Okay. Huh? Wow. You just you mean the half of it will add up to P? Try. Try. Okay, let me see. Can we try that? Okay, I think we can try that. Okay, so let's go to a further up number. Very good imagination. But then it's already not working for P equals to 3, right? Yeah. Yeah. Okay. Okay. So for P equals to 11, you can do as homework. But for now, you can see that there's a symmetry here. And then comes in 2, comes in pair. So far. No, it's not. Okay. There's no coincidence in mathematics. So that's the real fun of mathematics. We're gonna explain every coincidence. We're gonna prove every coincidence. Okay, so definition. So if m is a positive integer, we say that a is a quadratic residue of m if a and m are relatively prime and x squared congruent to a mod m has a solution. Okay, so this a here is what we call a quadratic residue. If it comes from some square, if it comes from some square, then it's the quadratic residue. If x squared congruent to a mod m has no solution, then we say that a is a quadratic non-residue of m. So for example, in this case here, let's look at the p equals to 5 case here. So in this case here, we'll say that 1 and 4 are quadratic residues of 5. Yes. Okay. And then maybe 2, 3 are not quadratic residues of 5. And then, okay. You cannot get 2 and 3 by squaring some number. Does that make sense? It has no solution to x squared over. Okay. We don't discuss about number 5 because the GCD of 5 and 5 is 5. Okay, we already discussed about the integer that they are relatively partially. So far, okay. So far, and get quadratic residues. It's something coming from a square. If you don't come from a square, then you are not quadratic. You are not the leftover quadratic operation. Okay, maybe to test you. Okay, maybe to test you, I could ask, what are the quadratic residues of 7? 1, 2, 4. Okay, good. Okay, good. So that's it. Right. So how about shall we do this? Can we skip this? Let's skip this. Okay, as a homework. I think you know what am I talking about already. Okay, so here's the theorem. Let P be an odd prime, okay, and A an integer not divisible by P. Then this congruence has either no solution or exactly 2 solutions. Okay, either you can solve it or there are exactly 2. This is similar to what we had in our real number system. Okay, so for example, x squared plus 1 equals 0 has no solution, or x squared minus 1 equals -1 has no solution. Okay, but if you're gonna have a solution, it is always can be you have a formula, right? Do you remember the quadratic formula? X. So if you want to solve like ax squared plus bx plus c equals 0, the solution will look like x equals to minus b plus minus square root b squared minus 4ac over 2a. Is this one? Yeah. So there are two solutions here. Okay. Well, you need to make sure your b squared minus 4ac is greater than or equal to 0, because you don't want to have a complex thing coming out here. Okay. Yeah. Okay, so this is very similar. So in this whole series of our number theory, right, is a discrete version of your calculus. Okay, discrete version of your calculus. Okay, let's not prove it. Okay, let's keep our tradition. I'll let you see first. Let you convince yourself. Maybe I can prove it to you next time. Okay, but then you sort of see the two solution already, right? Just now, if x naught will solve this equation here, then the other one that solve it is what? Minus x naught. Then you sort of see this thing happening just now. Correct or not? Okay. Yeah, right. Just now you see this. If one can solve it, two can solve it, minus two also can solve it. You solve it, minus two also solve it. Okay, you kind of see this two different solution already. And the other thing is, the other thing is, if P is an odd prime, then there are exactly P minus 1 over 2 quadratic residual of P. And P minus 1 over 2 quadratic non-residual of P among 1 up to P minus 1. Okay, so meaning half of it, okay, P minus 1 will be throwing out the P terms, the 0 term. Okay, so it just saying that half of it will be quadratic residual, the other half is special. Half of it, yes, half of it no. So let me see, is this a quick proof? Yeah, this is a quick proof. Okay, so okay, let's do it. So this is a very quick proof. So the proof is actually there are only P minus 1 thing you need to compute. So there are P minus 1 squares to consider. And by the previous theorem, right, there are either no solution or there's exactly two solutions. So previous theorem. X squared congruence A mod P has two solutions if exists. Okay, so in this case, they are exactly P minus 1 over 2 quadratic residuals of P, okay, among the integer. Maybe you want to argue that why these P minus 1 over 2 are different. Okay, maybe you want to argue that why they are different. Why are they different? Why are they different? Suppose they are the same. Okay. So next thing maybe I won't tell you yet is prove that. Oh my goodness. Prove that they are different. Okay, if they are different, then we are done. So basically, is you take this number, okay, so fix P, take this number, square it, okay, And then because every solution here will have exactly 2 solutions. Okay, so it reduced to half of it. So half of it is here. Then reduce to half. And then next you argue that, oh, this 3 is different. Then this half will be different. Then that's it. Okay, or this solution is unique, or you want to prove it like that, also can. Okay, these will have a unique solution, also can. Okay. Yeah, so let's see how this helps us. So maybe for this question, so among the integers 1 to 400, how many of them are quadratic residues of 401? Okay, so if you're gonna use so now you're gonna count how many of them, right? I'm not asking you which one are the quadratic residues. I'm asking you how many of them. Okay. Just now the theorem works if P is an odd prime. Okay, so if you can prove 401 is an odd prime, then you can use the theorem. Okay, so is 401 an odd prime? It's odd, definitely. Is it a prime? Okay, so to test it as a prime, you need to test like up to 20 or 21, right? Because the nearest perfect square is 400. Then you test it. In the assignment, you said that it doesn't divide. You didn't show me. You just tell me it doesn't divide. Okay, so that's one thing I want to mention. Okay, so if it doesn't divide, some of you will say that 401 divided by 2 is like 200. Maybe some of you write in a decimal place like that. Okay, it's not acceptable. Okay, but I want you to imagine that at the old time, right? People don't write fraction yet. Okay, so maybe you can write something like 401 equals to 2 times 200 plus 1. Okay, so this is the thing that you learn here. Okay, there's a remainder and division algorithm. But I don't penalize you, okay? But then try and learn this kind of way of stating things because we really prefer multiplication and addition only, okay, in mathematics. Okay. Yeah, so how many of them? So let's say if we prove that 401 is an odd prime. Okay, so how many of them? By previous theorem, there will be 401 minus 1 over 2. So there are 200 of them. Okay, that's it. I think I won't ask you to find 200 of them. That's too cruel. I mean, which 200 of them? Okay, so far okay or not? At this stage. Okay, yeah. We don't quite really do things with it yet, huh? So, okay, so the tempo of the mathematics is like this, and we will give you some tools, and then I tell you what's the property of this tool. Only I tell you how to use it. Okay, but this is quite different from the real world mathematics, where we start from what we're going to solve, and then we develop these two. Okay. So the presentation is a bit of a backward. So that's why some people don't like maths. Maybe it's this reason. Because when they look at this tool, they think that why do I learn this tool? So they are stuck with why do I learn this tool? Not going to learn it yet. It's true. This is very true. Because I really got quite a lot of students. So they are stuck with I don't want to learn it yet. But when they realize that they want to learn it, it's already week 15. This is very serious, I tell you. This is very serious. This is very true. It's not just mathematics, I think. It's also applied to all your courses. And so try to learn first, and then you will see why you're going to learn it later. Okay. But then, yeah, thinking of why you want to learn it is still important. I'm not asking you not to think about it, but don't make it a problem to you. Okay. Okay. So next theorem, let P be a prime and R be a primitive root of P. If A is an integer not divisible by P, then A is a quadratic residue of P if, wow, so many things here. So how to read this statement here? So if this is true, so if A doesn't divide P, then A is a quadratic residue. Actually, this if haven't finished yet, still got more if. Okay, so how should we read this? Okay, this is very painful a bit. So if A doesn't divide P, then there's actually two things could happen. Okay, so if I write like this, maybe make things easier. So A is a residue, quadratic residue of P if the index of A is even. Okay, and then it's not a quadratic residue P if the index is. Yeah, does this make sense? Does this make sense? What is the index? What's the index of A? What does this mean? So this is what? Still remember I told you the logarithm between index equation and the logarithm equation here? Okay, so this was tells you about what is the power of R, right? So that you get A. Okay? So if this power is even, what does this mean? If it is even, then it is R to the 2k, right? But then this is what? Rk to the power 2. So you are a solution to a quadratic equation. But then I think this part is quite hard, I guess. If it is odd, then it is not. This part I think a bit harder. So yeah. Okay, so the other direction is harder. Yeah. If it is even, then it's very obvious that what's the solution to this quadratic. But if it's odd, then how do you show that it must be? It must not be. And the other part is a little bit harder. So, shall we do this? Okay, let's do this and then we can break here. So let's do this. So what we want to show is if in R A, okay, I left with the A. In A is odd and A is not. Okay, instead of showing this, we will show the contra positive. Okay, so what does it mean here? So it means that we're going to show if go the other way, but do a negation to the opposite statement. If A is a quadratic residue P, then in R must be even. Okay. Everyone can get this logic. P implies Q, and not Q implies not P is the same. Everyone can get this logic? Maybe I want everyone to get this logic. If you don't learn this proof, but you must get this logic. So what's this logic? Think of one situation. If I'm hungry, I'm gonna eat. If you're not gonna eat, it means that you are not hungry. This is equivalent. If you are gonna eat, if you are hungry, you are gonna eat. And if you are hungry, you are not gonna eat. These two is not the same. It's not the same. Okay. Or if you are hungry, if you are eating, then you are hungry. It's not the same. Okay, so let me write down. So very interesting stuff happening here. Okay. Let's get some things out. So P implies Q, and then not Q implies not P, and then let's talk about Q implies P also. So if I'm hungry, then I'm gonna eat. If I don't eat, then I'm not hungry. And then the other is if I eat, then I'm hungry. Okay, so these two are the same. Okay, top and bottom is the same, but then left and right is different. Okay. Hmm. Okay. So top and bottom, I think we discussed already. Makes sense, right? If you say you are hungry, then you must eat. If you don't eat, meaning you are not hungry, because if you are hungry, then you will eat. But the other way is if I found that you eat, then you are hungry. I don't know it's true. You understand? Because I don't know why you eat. Maybe you are not hungry, but you're still eating. Okay. So you cannot imply this. If you are hungry, then you will. And because maybe you gonna eat is because other thing. Because my mother asked me to. Okay. So they are not equivalent. Okay, but top and bottom is equivalent. Okay, so this is a real daily life logic. I want you to get how to say, get familiar with, so that you are not being PUA by the others. Because sometimes they will use wrong logic to convince you or to side for you. Okay, so you must be sure on what they are talking about. Does that make sense? Yeah. Don't try get fooled by others. Okay, so we're gonna prove this. Okay, prove the other direction. Right? So we're gonna prove that if A is a quadratic residue, then prove that it's not odd, which is it is even. Okay, now we're gonna do this. So then there exists an x in z such that x squared congruent to a mod p. Okay, because a is a quadratic residue, so meaning it comes from some square. Okay, it comes from some square. So please. But then what this means, it follows that in of r of x squared is equals to in of r of a. Okay. But then what do we know about this in r x squared? It works like log, right? What can log do to x squared? You can pull the power down. Okay, so we can pull a power down like this. But then if I write like this, what happens here? Can you see what happened? I have managed to write in a as a multiple of 2. Okay, so here. So this implies that implying in a is even. Okay, because I write it as a multiple of 2. Does it make sense? Okay, yeah. Okay, so the corollary here is this. Corollary means what's the consequence of this lemma? With a very quick step. Corollary here is every primitive root of an odd prime E is a quadratic non-residual. Okay, can people quickly think why it is true, given that we know that if in A is even, then it is a quadratic residue. If in A is odd, then it is not. Can people quickly think why? How to use that statement? You want what? So our logic here, you want quadratic non-residual, right? That theorem tells you how to get quadratic non-residual. If the in A is odd. Okay, do you get in A is odd here? What is the property of primitive root? Do you remember? Let's call this A here. What's the property of primitive root? A to the what? Pi K congruence to 1 mod P. Okay. What is phi P here? What is P? P minus 1. Good. P minus 1 is prime or is even or odd. It's even, huh? But we want odd. Huh? But then, can you multiply A to both sides? What do you get? A to the P congruence to A mod P. So it comes from some odd power of A. Comes from some odd power. Okay, so in A, here is putting A also is P, which is odd. Okay, makes sense. Okay, so this A is this A here, if you like. And then the green A is the green A. Does that make sense? Makes sense. Doesn't make sense. No. Yes, no, no, yes, yes, no. If not make sense, you can ask one. Doesn't matter. I could be wrong sometimes. Maybe I always wrong. Yeah. You have to question me. You cannot think that every teach here is correct one. They could teach you wrong stuff, then you will drink the wrong stuff forever. Yeah. And so you must question. Makes sense to you. The first day I go to class, I mean, the first semester, the most frequent word I heard from my tutor is make sense. But then I grow with a Malaysian education system, right? They didn't say what is make sense one. They just said do like this, do like this. No make sense one. Although sometimes like I will ask why you do that, why you do that. But that's not the most important thing that what the teacher want you to do, right? The teacher just want you to write this answer. Write this answer for me so that I can give you full mark. You understand or not? So you have to make sense to yourself. And I'll try to make sense to you. Okay, so come back here. Any question? Any question? I'm applying this theorem here. Okay. And then why this theorem works, I just prove it to you. Okay. I'm applying theorem here. Okay. So to say that whether it is a quadratic residue or not, go and ask what's the in A. So go back to chapter 4. Then you go back to chapter 4. Because this primitive root exists, right? Because we're only considering prime. Yeah, prime here includes what? 2, 3, right? So 2 is an even prime. And for the rest of the all prime will also can settle, so there's the primitive root. So you can solve using it. Make sense? Yeah. Okay, so it's very interesting about this theorem is you are asking a question about quadratic residue, but then you are turning this problem back to primitive root. Okay, so this is the power of this theorem. Okay, you are asking about if there is a square and a square to A, and if there's a number that's going to okay, to talk about the index, okay, index of A. Okay. Yeah, right. Okay, because you see, this R here is primitive root, right? So in our case here, this R here become A because A is the primitive root that we consider. Right? So that's why we have a in AA here. So this is the R that we consider. This R is a this A is a primitive. Okay, because from the idea of primitive root, we can get this congruence. We just multiply A with constant. Okay, so P is odd, then by previous theorem, A is not. Huh? What? Okay, so far so good. Okay. For the back, is it okay? Okay. So before we break, let's talk about this Legendre symbol. So instead of talking about whether it is or not, we will introduce this new symbol here. It's like a fraction, fraction with a bracket. Okay. So we will name this symbol as 1 if it is a quadratic residue, and if it's not, we put a minus. Maybe you can ask the question, why not put 0, put 2, put 100, put 11, or something like that. Well, because there is a structure inside there such that it can be captured by just looking at 1 and -1. The parity here is important. For example, -1 times -1 becomes 1. So you can imagine non-residue and non-residue become a residue. Something like that. Okay, so the structure here is captured by this 1. Okay. And if you put 2 or -2, then your number will get larger and larger, like 4, 8, right? But then you haven't defined what's 4, what is 8. But then here 1 and -1 is very sophisticated. If you multiply together, you get -1 or 1. Okay, so the parity here is important. Okay, any question before we break for next hour? Maybe in the next hour we'll just discuss assignment. Have you guys tried the tutorial question? Anyone try? Problem set. You got one? A little bit? Okay, good. One of you? Anyone else try? Huh? Only one try? Wow, this is very dangerous. Okay. I encourage you to try. Maybe in the last class, we will do a revision class, then we will discuss the problem set. Okay. So you could try the problem and then identify which one is harder or which one cannot solve. Then we can do it together in class. Yeah. Okay. Try. If you think that it's easy, maybe you can just try one of them or two of them. Okay, and then if you can manage, then you skip the others. Okay, so let's break until 5:14. Hey, 我上火啊，上火上。哦，sorry，对，你讲的对，你讲的对，对，你对，也
我要去找屁股。
谢谢。
230，那个很便宜的那个，哇，错，哇，这么仔细的在研究。当年还会拿一个笔记本那里写，然后我就不会 GPT。大一的时候不会了，大二的时候开始跟 GPT。大一的时候是老师讲听得懂，然后大二的时候是记笔记能听得懂，那个时候是被学回就不行了。SVD 那里其实也还好，我只是觉得那个大一那个我是一节课没有，就叫什么 老师不是两个从来过，他那个老师讲的不是个太多东西，是在这儿，所以他要我跟你是个老师，是的呀，是的，对，我觉得他一下问一下你像完全在情况，是我的感觉。没有自己的地方，没有语言水平。那韩语怎么说？我上次就是把它给我这2年，我觉得我学的就是这韩语，我的习惯韩语。
证明不重要，就是那会好吗？还是说会证明？
感觉不会吧？你做的习题感觉会像证明还是不太？OK，这样应该
这题感觉有点像那种，
有一点比较抽象一点点的，没有数字哈，你的感觉。真的，但是你觉得我们教过的东西，你可以来推出这些东西，还是啊
证明那些文字的过程，我可能写的不太好。
？OK OK OK OK，但至少 OK，但是至少说有用到什么推专什么 OK，
到什么
对
定义吗？
对对对啊，对对对，
我有时候可能就是会写
漏掉
出来，但是我会忘记那个定理的名字。
啊，其实名字还不一定重要，但是就是定理的那个先决条件跟它的那个是很重要。因为我们也没有给那些天人名字，所以你比较好的是就是怎么确认你有没有引用的定理，就是你一定要有它的条件存在，然后就是说这个条件有了过后就有这个结论。
是加那个地的，是个书写。
I mean like yeah，
写掰什么 C
对
O
对
N，
对
然后
对对对，
我可能中间那个词我可能会写错啊，或者忘记，就是
中间的词还有什么词？
就是那个那些人名啊，
人名，
对，
人名有人名吗？
有吧？那个什么
哪一
费姆，
哦，那个比较出名的你就要知道，比如说 Fermat 里的铁人嘛，铁人嘛，这种比较出名的你就要知道。
就是也要写上去这样。
呀，因为你写那一个的意思就是说，我不用再告诉你那个句子是什么，就是我不需要告诉你它完整的句子是什么，我只要告诉你，
就是把它那个定义成
对，名字出来，我就知道那个 statement 是什么。
好像总要记的名字会很多。
应该不会吧？差不多要结束了，应该不会，应该不会，应该不会。
你写字
OK，好，没问题。你看不懂，你直接指出来。
它这个
好，等一下我会解释。等一下我解释，我解释完你看一下，还有个什么？
我说这个是作业里面的，
对，
就是我其实上次有问你，就是那个这个是我就是用带用句的方法算出来的。
哦，OK
答案
OK，
是对的，没错。但是就是我当时编辑文件的时候，我忘记把这个中国设计定理的放进去了。对的，
那就
那这样子的话，
有一点难嘞，我不能够来，
这个
对，
那好吧。
好，OK，没问题。等一下我们再讨论一下，你看一下怎么样？
就是第一题他说了，你就算到这样子就不用再算了，是吧？
第一个
对，第一题他不是说就是说可以把它，
拆成 prime factorization，
对对，
呀，
那这样子就不用算，不用算到那个整个结果，
结果是
就说不用把这些都解开，然后给它算出来，就是
哦，好像是吗？他好像是这样写对吗？
对，
呀，
不用解开这种，
呀，不然的话这个应该很大门啊。
对，
对
就是算了半天。
对，是对。Okay, before we start, let's take attendance. 郭书月、石杰生、范家豪、李承炫 ，Yes，周恒婷、朱祥哲、任波、易涵、思颖是吗？韩思颖，Anyone is a friend of 韩思颖？Haven't seen her for quite a few times. 韩思颖、刘正贤、张同俊、陈子涵、王金珍、孔一佳、竞争孔一佳、郑子涵。哦，I miss one，亚伟彤、陈子来听还说，OK。 崇瑞、陈思曼、何嘉诚、何嘉诚、丁真个、浩云、OK，浩然、浩云 here or not today? How in here? Seems like I don't see him. How in? Yeah. Okay. 陈心怡 yes. 田文琪 OK. 张小柔、张泽瑞、陈凯莹、凯莹。Okay. I think both of them here, Tiffany and Kai. Okay. Check it. Yeah. Yasin, Jasmine, you saw them. Jajin. 梁家悦，卢泽新、韦明涛、杨旭成、曾一飞、陈玉清、李林义、曹化元、王雅、李浩聪、刘义书、潘子良、甘金浩、郭明轩、李明翰、李伟翰，OK。Saudi Ayub, okay, good. Joy Lee, where are you from? Sorry, Tunisia? Okay. 何明浩、黄棋子、秦子祥、熊培成、张馨予、周瑞敏、赖文义、陈子睿、李小环、曾天健、Sim Aaron Fabian、孙瑞全、Isaac 有西宾客 ，OK， 高硕呀，王诗涵、王思怡、车明宪，双分没有来哦。李心凌、林家泰、林卓娜、陈家福、关冲铺、崔文倩、林畅旭 ，yes， 宋浪凤、小佳、赵泽宇、T 收视，OK。陈少涵、陈卓、乐山、一成、星辰、诺，应该说诺 ，OK。黄玉涵，彭玉兴，玉兴，彭玉兴，no here。Studying here now. Okay, good. Okay, before we discuss about assignment result and assignment, I still want to talk about this logic a little bit. There's some thing I want to mention here. So I mentioned that P implies Q is not equivalent to Q implies P, right? So meaning if I'm gonna eat, then I'm hungry doesn't imply that I'm hungry, then I'm gonna eat. This thing is actually happening in our real life very often. What do I mean by that? If I'm gonna eat, then I'm hungry. That could be true, but then people don't always eat if they are hungry. You know, that's why there's a situation like the parents will take we call the rotan or the stick and store their kid. Hey, hungry already. Now is the time to eat. Why don't you? Okay. Also, another thing is, Did you see some social news? It's like they play games for 4 days non-stop. They don't know they are tired, but they admitted to the hospital, and then the mother say, no need to save my kid anymore. Did you see this news? You see it? Only one of you see it? What the other do? Huh? You see this news? Okay, actually. Wait, let me see. See? Oh, here, I found it. But it's in the Chinese form. For those who cannot read Chinese, I will translate for you. Basically, it's okay. So, university, male university student, okay, 熬夜 can't stay up late. Okay, stay up late, and then continuously play games for 4 days. Wake up, go to the toilet. Okay, this is I Chinese, and then fall to the ground. And as the mother say, just leave it. Okay. I mean, you would think that this mother is very cruel, but then you go and read the news itself. I think the news is not savable. I guess even if you save the kid, it will be problematic. Maybe I'm not sure. I just read the headline. If you're gonna save that kid, you still need to stay alive with a lot of apparatus. So just let it go. Okay. Yeah. Yeah. So it's almost like cannot save already. So that's why they let the kid go. Okay. So if you if you stop playing, it implies that you are tired. But it doesn't imply that if you are tired, you stop playing. Correct? This kid doesn't stop playing. Play until die. Okay or not? Make sense? Okay, very true, the logic. So this is a very social problems like this. Yeah, so be careful. Hey, did you know that our school actually there's a case done before? Maybe for new people you don't know, but for the old senior you should know. There's someone also play game fall down and then. That's why you see every our building has this apparatus called AED, sorry. AED. Okay, so that's why you see AED around. Before that, there's no AED in our building. Okay, so after similar similar case happened, then we have AED around. Okay, be careful. And also because you are alone here, if you disappear, whatever, then we don't know. But luckily now our hostel all become couples, right? No more singles. No more singles, right? You still have singles too? No, right? Yeah. So if it's single, then if you disappear, then people won't realize one. And it's very hard to realize. Okay, so please take care. If you come out so far and study, and then you can go back. Yeah. Yeah, very important. Take care of your friends. Okay. So let's go this. Yeah. So let's discuss about assignment. The result actually is pretty good, very good actually. The average is like 40, about around 49. So everyone will get an A, is it? Hopefully you guys get an A. So let's discuss what I want from your assignment. In the meantime, you can chat with me or ask me if you're unsure. Okay. So after discussion, you can come to me if you still have problems with your mark. Okay. So there are basically 4 questions. Okay. 14 plus 12 plus 12 plus 12. Then there are a lot of small part. So first part, 1A is determine whether an integer 1321 is a prime. Okay. If the n is composite, if the number is composite, write down its prime factorization. If n is a prime, list all the prime number you need to check. If it's better, I think we should put a comma here. Okay, well, I think all of you are very good with listing down whatever prime you need to check here. Okay, you pick the nearest square, perfect square, and then work out the prime numbers. But something that I wanted from you is you didn't show non-divisibility using division algorithm. Okay. So I also just take off like 0.5 marks. Yeah, very minor marks, but I want you to show whatever you claim, okay, try and show it. You say that something is not divisible. Show it. How to show it? Show that there's a remainder, okay, after dividing. This is how you show. Okay, quite a few of you do this. Okay, quite a few of you do this. There are a lot of you, I mean, like maybe 10 or 8, getting full marks, okay, 15 marks. But most of you, I think you don't do this. Okay, so also a lot of you get 29.5, just this part. Okay, so my idea is try to show whatever you claim. Okay, if you say it's not divisible, why? You ask me to compute for you, right or not? You should compute for me, man. Okay, you show that that's not divisible because there's a remainder. Right? Okay. So another way is you put decimals, right? Okay. That's not an ideal way in this class, but I'm not penalizing you. If you can, try to learn it this way. Okay, write down the remainder. Not the remainder divided by this number, the device. Okay, this part I think is good. No one said this is not a prime, so it's good. Safe. B, I think B is a very straightforward now. Okay, write down the prime factorization of A. And then write down the prime factorization of B. Basically, you just simplify B and then write down the factorization. Okay. Okay. Maybe the trick here is like what we did in class, right? Maybe you could forget to write down the prime factorization for 8R, 6R, 4, right? But I don't think anyone is doing that. So you guys realize that 4, 6, 8 is not prime, is it? You realize? Is it? Or what? Or ChatGPT 2.0? Yeah. Okay, hopefully you realize that there's some composite number here. You need to split further into prime. But then I think some of you confused with prime factorization. You thought it's just listing the prime factors. Okay, it's not. You have to list it with this multiples. Okay. Right now, in the form of multiple. In the product, sorry. Okay, in the product. Okay. 3, 4, 5 is kind of straightforward. Okay, you can use the, what do you use? Use the formula, right? Greatest common divisor, you take PI to the minimum of AI, BI, and then LCM you take to the maximum of AI, BI. But some of you very cute, you do Euclidean algorithm. But this Euclidean algorithm is very long, okay? I think he or she is wrong, I guess, in the end. So please don't do that. So you need to think why we ask you to write down the prime factor. Because we want you to use that formula. And don't do Euclidean algorithm for such a big number. If it's correct, then good luck, but then if not, then bye-bye. Okay, this is it for this 2 things. So for the next part is this, use the Euclidean algorithm to find it. Okay, yeah, so this part is using Euclidean algorithm to find GCD. Okay, this is small number, so can do it. And then part B, backward Euclidean algorithm to find D as a linear combination of M and N. And then explain why differential equation doesn't have solution, because you talk about the divisibility of the GCD, right? Okay, with the 3 number appear across. And then solve D. Yeah, D, any problem with solving D? I think people are good in solving this. Yeah. One thing is not good is maybe people will forget to put this. Okay, so please remember, tell us that what happened to these variables. Okay, so it's very important where you pick this. Okay, so this is it for this question. For three, very good. You guys know how to put set notation here. You know why? I mean, like, why do you put set notation? Because in class I put. Okay, only one guy. I found one guy didn't put. Most of you guys put. Okay. This solution also not good. Okay, so I put it for him. Okay, so you should put a set notation here, because this system here is a set. Okay, if it's a set, then we will put a set notation. No one give a weird answer. All of you just give 0. Okay, you don't pick a different solution. Okay, never mind. You don't pick different representative. So for B, C, D, we penalize for you if you don't mention remainder last digit. Okay, because you are not answering the question. You are just trying to compute the thing you like to do. Okay, so make sure you write down after you compute what's the remainder. Okay, remember to answer the question. Okay, you understand? Okay, so this is very common in real life. You just do something, but then you don't answer problems that people ask. Okay, so we take off 0.5 marks. Okay, if your answer is correct, but you don't mention like last digit, remember. Okay, but then I think all of you know what to do. I think it's the only thing you learn what to do, right? So if you want to find remainder when divided by 9, you just consider mod 9. And then you want to find the last digit, you consider mod 10. Again, you consider remainder divided by 7, then you consider mod 7. So far, I think so good. Yeah. Yeah, any question? Oh, I guess this solution, I mentioned about the period that one of our friends here mentioned. What's your name? What's your name? Okay. Oh, what is it? Yeah. So you mentioned about period, right? I think this is what you can. If you want, you have to write. So these will tell you the period is K, right? 4K plus 4K plus. Although this solution isn't prove to you. Okay, but you cannot just infer by looking at the first 5. Yeah, unless you can write out this strong separation. Okay, no? Yeah, so the period here is this 4K that you mentioned, and then 0, 1, 2, 3. Didn't prove it to you also. Okay, unless you can mention this, we can give you. This is the way to write it. Maybe you can discuss if there's too many marks got taken off. We can try and discuss that. Yeah, okay. Then for D, I think most of you are very good. You realize that if this K is greater or equal to K, then K factorial actually divisible by 7, so that disappears. So you just care about 1 factorial of 6. Okay. Yeah. Okay, and then you should do the normal simplification here. Okay. Lastly, okay, for the question 4, for this question. For this question, it's not quite in the setting of Chinese remainder yet, right? Because it's not the same X appear Okay, it's not the same x here. So what you do, you need to do some take inverse. Okay, you take some equivalent operation here, which is taking inverse. And so you need to find the inverse of 3, inverse of 8. Actually, not inverse of 8, right? Because 8x will simplify to x mod 7, right? No inverse. But then 2x, you need to find the inverse. I don't know. Is it true? This step, the step that mentioned here is like telling you why is Chinese remainder works. Otherwise, I think you need to take 3, the inverse of 3. I think it's 3, right? It's 3 in this case. And then here, actually, you can straight away reduce to 7x mod 7x congruous to 1 mod 7. The above is mod 4. And then the bottom is, what do you multiply? 5. Okay, inverse of 2. Then from here, you can use the Chinese remainder theorem because it's the same thing that solve different equations. Okay, you can use Chinese remainder theorem. You can use formula, okay, that I told you last time. But then, what's the problem here? The problem here is people forget about the mod. Okay, they don't put the mod 252 here. Okay, so remember that your solution is only unique up to this mod. Found a number, but then it's only unique up to this mod. Some of you could write something like this. I accept. Actually, this is the definition of mod. So you write like this plus a multiple of 252. This one also work. Okay, yeah. I accept this because this is exactly what mod means. Yeah. So far, any question? You're not sure about my marking? You can ask now. Because maybe others will confuse at the same time. Can you ask? What's your problem? Any problem on my marking? Yes. You can't do your answer question. Okay. Is there a general question you wanted to ask? Not really specific to your answer. Okay. How about the rest? Any general question you want to ask? Not sure how to answer. One more thing is please put down your name and student ID because I already listed out in your question paper. If you don't use my question paper, then you need to write down your name. Otherwise, if we get lost, we cannot identify whose piece then. And please always write down your name and student ID. Any question? Other question? No. Yes, yes. 我再发一次。这样子不用，下一次就写这样。So please do it starting assignment 2. Put down your name and student. It's like your exam, right? You need to put down your name. Yeah. Your identity is very important here. Yeah. 都写。都写。Files I need to remind you. Think not much, I guess. Yeah. Actually, I prefer teach in short sem. You know why? You know why? I prefer to teach in short semester. 为什么？每周3节课，没有啊？我long sem也是每周3、4节课一样。Because in short sem, right, it's selected by you, so you take initiative to learn this course. Yeah, so long sem is very different. Long sem is like they have to, either they like or not, they have to study. Yeah, no option. So they will be not taking initiative. Not to say lazy, but then not motivated. Okay, so in general, the student for short sem is better. I mean, I wouldn't say the students itself, but himself or herself, but the student quality will be better. Okay. Even if it's not good enough, but then he or she will try and do it. This is the difference. Okay, between short sem and 啊，这个是强的，很难抢啊。OK OK，好，有没有人卖黄牛啊？没有咩？哎，我听说 Game Theory 哦，一个位置卖500块哦。我听说啊，我听说。
好像是有人在卖。
哦，啊，我300码，真的咩？
你留2个位置
是真的还是假的？是真的啊。
这么值钱？老师，你靠阳贵些。
我柜子。哦，原来我科值300码。好。可以。好，非常好。对 ，Yeah. But then, yeah. But yeah. Okay. Any other question? Yeah. Okay, good. Know how to work for the next assignment? Okay. Okay, know what to write for the next assignment? Okay. Yeah. Okay. In that case, maybe we can break earlier today. Yeah. Okay. So see you on. If you have any more problem on your assignment, you can come to see me. Now.
学校的网是最有趣的。
Oh yeah. Or because you didn't answer whether it's a remainder or last video. You just show working without answering. No, it's not obvious. It's not obvious. You have to mention it. Yeah.
我直接对，只要是对我用的阶段。
Oh no. If it is a theorem that we introduce, you can use it. Unless we ask you to show that. 我进不去，该看了。
刚开始走了。
对呀，因为这个不是这个的意思，这个的意思是这个，就是这一行东西吧。啊，就是这一行东西吧。这个叫做 prime factorization。
这有2、3、5、7。
没有，我的意思是说 A 写成这个的意思啊，不，sorry，prime factorization of A 的意思就是 A 写成这个形式。明白？
我也用了。
然后再看。
但是我是
有些那是会，那跑要写满那 X。
没有，他要写成这个乘法的形式，就是
2乘3乘5。
对，就是那个来的。啊，你这个只是在 list 它的 factor 出来。prime factorization 就是这个东西来的，你就把它 factor 成 prime。
所以我写大概写2乘3乘5乘7这样子。
就是这行东西其实就可以这样。这行东西。
我哪一个？哪有？
再来。好，
老师对，我考试的时候，如果我的做法是跟 assignment 这样子 OK 的，还讲我要写很多遍。
就我现在要求什么，你写什么，你就会。
这就 OK 了。OK 好这样。
我这个扣分是因为没有写。
啊，对，没有错。
那这个就
扣你几分？
扣了3分。
这几分啊？这几分？第2题、第3题，C 4分啊，我扣你3分。
对，
我想想，这样的话我给你。
我上面没有证明。
你其实也对你对，一个是没有证明，但是这个答案也没有证明其实，但至少他有写出来，对他写出来你想讲的东西，对，我可以给，我觉得2分吧，我可以你给你2分。加1啊，加1 ，OK 吗 ？OK。
这个。
好，这个这个对，这个这样的话你是少写了这个的 inverse 也没有写出来。
对，我在这写了一个，然后我就 写了一个之后，然后我就去
因为你哦，你你这 find inverse 我不知道你 find 谁的 inverse。
哎，
对吧
对，我写了一个
OK，至少写一个哈，我给你几分。哎，不然去一下你的文件夹，我看一下你叫王他姓什么？
王。
一直的 OK，我先去你的文件夹，给你加分，这条文记句。这里加。好，那个的话，我给你填完10分哦，10分哦，这个只有扣2分罢了喂。我觉得，翻译 verse，你的答案对。然后你再做摩擦性高低的吧。为什么你有4K 加3呢？哦，因为你放进来这边接。
对，没有用。
所以其实我扣的其实就是这里啦，其实就是来，
我也不
不跳，But then 呢，我想想，好的，给第12行程扣2分，因为刚才是3分是32。OK，我加你1分，我加你1分。OK， 好，好。哦，OK 呀。
我把它做成一个题目。
可以啊，就像我们也是可以。Question 2 OK，可以。什么叫 position？
position 就是那个 letter 的。
了解。
还有这个是要讲 state 你那个product。
对，不用算出来。
答案也是把它算出
哦，
来。
你也算出来 ，OK，不用紧，这个比较重要。后面那个比较重要。
这可以。
OK， 好，可以。
How detailed do I have to be with my step?
Sure.
This is my essay.
Okay.
The question. Answer is just 2 to the 29 modulo 95. Do I have to write the steps or can I just write the answer like this?
You mean you have a multiple letter to do this, is it? Or you just need to do for one letter, or you need to do for
this is the
lot of
one
letters?
with 1 letter.
Oh, this is the one with 1 letter. Then this is good.
This is fine.
Yeah, this is
I
good.
don't have to write like 2 to the 9th is 512 and then 512 modulo. Like I don't have to write the steps for solving the modulo.
Oh, it's better. I mean, you should.
I should.
Because it's impossible that you compute everything first, or only you do more, right? You should be like doing like grouping view and then like what we did in class. You should. Okay.
请将话筒放回。
Yes. I have a question.
请将话筒放回。
Oh, sorry.
请将话筒放回。
I don't see what's wrong in this answer. You subtracted 3 points.
Let me see.
Yeah.
It's 3 points.
Yeah.
The final solution is wrong, right?
No.
Yeah, I just kept it as a multiplication.
Wait, multiplication?
I think
it's not 0.5?
It's not point, it's 131 times 50.
Wait, you see this time is like very bottom. Wait, let me see. Let me check this.
It was here. I said we multiply both sides by 100 over 2. So it was minus 24 and I multiplied